Yeah, and I have to take this small thing inside. Okay, when I'm doing this, in fact, about 1 year, I was in Florence with some friends, Guillaume, Nabil, and Jean you were also here. And I had a talk to prepare, and the topic was open. And I didn't know the topic about which I could speak. And my friends, they told me, speak about something that you like. And then I think about that. And I prepared this talk about discrete tomography, which is really a field that I really like, and which is not very well known. Unfortunately, it was a 1 hour talk, and then I had to compress it in just 30 minutes. And that's a pity, but is it working like this? No? Okay, I will do like this. Okay, then I will start with a brief overview about what's discrete tomography in a few words. Then I will skip with the idea of the talk, which is to give an overview of the story of this small field. Then I will focus with the amount of time that I have. I will focus on one result, and I will end with one open problem from Nogales. Then it works. That should work, but okay. No, but it does not matter. No, but I will do without. Then what's the problem? We have some lines in the plane, and we have a subset of the intersection points. Then not all of them, but some of the intersection points. And for each line, we have a prescribed number of points, which could be a 2, a 3. It's an integer, positive integer. And then what I want to find is a subset of T with the prescribed number of points on each line. If you look at, for instance, this line, the request is to have three points on it, and we have selected 3 black points on this set. Then that's the general problem that we have. Of course, this problem is, as many others, NP-hard. But if you want to do some computations, you can rewrite this problem with an equation which is Ax equal to B. And the matrix A is the matrix of the characteristic vectors of your subsets, of your lines. And B is the requested number of points that you want on the lines. That's the more complex equation that we'll have during the talk. And then if you want to, if your dimension is not too big, if the size of T is not too large, then you can use a solver of integer linear programming to solve this equation, Cplex or Gurby, and then you can get a solution. Okay, and maybe if you are more interested in geometry, something that you can add is some constraints on your set. For instance, you can imagine that if you have selected these 3 black points, you want also to have something which is, in a sense, convex, and then you want to also have the interior points in the yellow triangle which is inside. Then you can also add some geometric constraints and think about this problem. In fact, the way to present this problem is a discrete tomography seen through the eyes of a computational geometer. Because usually in discrete geometry, people they are working in a more strict framework. In fact, people in discrete tomography, they pay attention to grids. Then you have the prescribed number of points on the lines, and you want to find the grid points which give you the projections. Okay, that's for the main idea of what's discrete tomography. Then I'm going to skip to the origin of this field. Why these questions? And I would like to mention these 4 colleagues, Alberto Del Lungo, Attila Kuba, Alain Dora, and Maurice Niva, who had a great impact on this field, and unfortunately who disappeared in the last 20 years. And if you think about the overall picture of discrete tomography, it's really a multidisciplinary area where you have some theoretical computer science, physics, mathematics, medical imaging, and all of these things are related. Then I start with the very beginning of the field. It's the discovery of the X-rays by Röntgen. We did the first radiographies, and it's the birth of medical imaging. In fact, Röntgen received the first medicine Nobel Prize for this contribution. And then that's the very beginning of the story. And 80 years after that, Hennenfent and McCormack, they had the idea to use not only one X-ray, but many to build this EMI scanner in the 70s. And this, for the story, this development of the first scanners, it has been helped by the money of the Beatles, because the Beatles, they were in the EMI company, then with all the money that they gave to the company, it was possible to develop these strange things, scanners. And what's the idea of the scanner? In fact, the idea is how can you look into an egg without breaking it? You don't want to do any omelette. And if you have one picture, one X-ray, you have an idea of what's inside, but it's not enough to have an image of the cross-section of the egg. But if you have multiple views, then you can start to do some things and to try to recover the cross-section of the egg. And that's exactly the problem that you have in discrete tomography. You have to solve an inverse problem to reconstruct the image that coming from the X-rays. And on the right, you have the first clinical scan with the EMI scanner. And when people thought about this problem, in fact, there were previous work in mathematics dealing with this mathematical problem. It's the work of Radon. Radon, in fact, he defined a transform, which is called with his name, Radon transform. You have a function on the left with two variables. And what you do is that you compute the sum of the function on lines, on all the lines of the plane. And the lines, you can parameter them with an angle and an offset, and that's the image that you have on the right. That's the Radon transform. And when you have this, the line sums on the right, the problem is are you able to recover the initial function f? And that's the inverse Radon transform, and Radon has shown that it was possible to do that. And a few years later, in fact, I don't explain how it proceeds, because there is a very simple way to understand how Radon transform works. In fact, if you have the Radon transform, you can compute from this the Fourier transform, because you have the sum of the function on lines. And with this, you can compute the Fourier transform, and then you just have to compute the inverse Fourier transform to get the initial function. Then that's very simple. And then, of course, in practice, you don't have the full data. It's not continuous, and then there are many algorithms which are doing this on incomplete data, and it makes the field of computerized tomography. Then, how are we going to discrete tomography? Then, to be precise on the vocabulary, we have this field of computerized tomography, which deals with the reconstruction of a continuous function, which is defined on a continuous domain. Then we have the field of geometric tomography, where you want to reconstruct a binary function, which is defined on a continuous domain. And then in discrete tomography, we are reconstructing binary function on a discrete domain. And this question, it was in the 90s, when a physicist, whose name is Peter Schwander, he had a problem. And his problem is that he started to work with some very efficient microscope. And with these microscopes, he thought that he will be able to count the number of atoms hidden behind a pixel. Then, in a way, he was able to count the number of atoms on a line. And the question that he asked is, with this data, can I recover the 3D position of the atoms in a crystal? Then imagine that you have these points which are in a crystal, then they are on lattice, and you are able to count how many points you have on each line. in this direction and with another direction and with the third direction, are you able to recover the data, the positions of the points? That's the combinatorial problem, which is exactly discrete tomography. And then he asks the question to an expert of computerized tomography, whose name is Larry Shape. And Larry Shape, he thought, oh, I'm not able to solve this problem. I don't have the tools for this. Then he he organized a mini symposium at IMAX, and he called it discrete tomography. That's the origin of the name. And then we had several research groups which started to work in the US and Europe, who started to work on this question. There was Maurice Niva, Peter Griezmann in Germany, Richard Gardner, and also Gabor Herrmann in the US. And then we have the birth of this field of discrete tomography. And when you start to work on a question like this, usually you have to look at the state of the art. Are there people who already thought about it? And then they've seen that there was a previous work from Reiser and Gale, which is dealing with a puzzle. It's a very simple puzzle. My son, a few years ago, I tried to train it to do this kind of puzzles, and it did this. And what's the problem? Then you have only two directions. You have vertical projection, an horizontal projection, and you want to recover the set. And Reiser and Gale, independently, they have shown that you can solve it in polynomial time. But in fact, nowadays, you can see the problem a bit differently. It's really easy to see that, to design an algorithm. In fact, you can think about your grid. Each point of your grid, you can see it as an edge in a bipartite complete graph. And then you can see your projection as degrees of the vertices on the left and of the degrees for the vertices on the right. And then you can design, you can imagine using, put a source on the left, a sink on the right, and reduce this problem to a problem of computing a mean cut max flow problem. Then you can see this problem, which is geometric as a problem of flow problem, as a flow problem. That's a useful tool. And then when they looked at the state of the art, they discovered also some other problems which are related. And one of them is timetables. Then we are going to 3D, we have this 3D grid, and we have some projections with on lines. And we can even imagine a 3D binary instance. And if you look at this problem, it's related to timetables. You can imagine that in a direction you have the teachers, in another direction you have the hours and the classes. And if you look at what happens in such a wet grid, it's the timetable of a teacher. And if you look at this two-dimensional grid in red, that's the timetable of a class. And horizontally, you have what happens at a given hour. And then, in fact, if you think about timetables problems, they are discrete tomography, but sometimes many times you don't have exactly equalities. You have some requests which you don't have two classes at the same place, in the same room. Then you can have inequalities instead of exactly equalities. And timetables problems, they are NP-hard, and even with some other constraints that you can imagine. And in the 90s, there was also another problem which has been proved to be NP-hard, which is a 3D work construction with equalities. It was in the framework of cryptography, where people they wanted to know if they were able to recover what's inside the 3D matrix from the projections. And it's NP-hard, again. Then we have these previous works, and then they started to work, people started to work on discrete tomography. Then I would like to present you a very nice result, which is a uniqueness result, but it's not uniqueness, we need some assumptions, in fact. Okay, then we have this first result with a polynomial time algorithm, and then we have this NP-hardness result. And if you think about some variants of this problem, of this 2D problem, you will get many NP-hard results. Some of my results, my own results, are in this area where you prove that it's NP-hard. Okay, and there are many NP-hardness results, and can we opt to have something which is polynomial time? And then people think, okay, but what happens if I want a solution, a set of points which has some geometric properties? Then the geometric properties that you can ask could be to be connected, for instance, or it could be to be convex. And I'm going to focus on convexity. What happens if I'm requesting my solution to be convex? And in particular, digital convex. What does it mean, digital convex? Digital convex, it means that this set, if you take this lattice set, if you take the convex cell in yellow, there are some holes, some missing points. Then this set is not digital convex. If you add the 2 points, 2 missing points, then this new set is digital convex. Well, that's the meaning of digital convex. And then we have this beautiful result from Richard Gardner and Peter Witzman. And also for the algorithm, Sarah Brunetti and Alain Dora, they've shown that for some directions, the solutions are unique and they can be reconstructed in polynomial time. Then that's the result that I would like to explain a little bit. What has been for some directions? Why for some directions? Because in fact, for some other directions, we will not have unicity. I took a set of directions, U, and if you look at these two sets, the black points plus the blue ones, or the black points plus the red ones, then they have exactly the same projections according to the directions of U. And what happens in this is that around the black points, you have this thing which we call a U polygon. If you think of the boundary of the U polygon, you have alternatively red and blue points, and all these blue and red points, if you look at a direction in U, you will find a point which is the other color. Then that's a U polygon. And in fact, the uniqueness is related to the existence of a U polygon. If you have a U polygon, then you cannot have the uniqueness property. Then the question is, do one U polygon exist? When do they exist? That's the question. And there is another one below. And then there is a very nice trick that I really like. When you have a U polygon like this one, what you can do is to take the midpoints of the edges, like this. And it gives you a new polygon, and then you can do it again, second time. And when you do this 2 times, then you get a new U polygon. It means that when you have a U polygon and you do two iterations of this, take the midpoints and relate them by edges, then when you do this, you have a new U polygon. And then you can think, what happens if I do it again and again and again and again and again? In fact, when you start from a polygon and you do this process infinitely many times, you converge to an affinely regular polygon, like this. An affinely regular polygon, it's a regular polygon that you do an affine transformation on it. And then, if you apply this to a U polygon, then at the end, starting from a U polygon, you will have an affinely regular U polygon. And these things is very constrained. There are a lot of constraints. Then you can say, okay, it cannot exist anytime. And that's the result that Gardner and Gritzman they've shown. They have shown that these U polygons, these affinely regular U polygons, they can only exist under some assumptions. The assumption is that you need the cross ratio to be in a small set of values. And if the cross ratio is not in this small set of values, then there is no U polygon. Then the result is that for 2 and 3 directions, you have always U polygons. When you have 4 directions, then you have U polygons only in the case where the cross ratio in these values. And when you have 7 directions, you cannot have U polygons. It does not exist. And it's a non-trivial proof. I don't want to detail it, but it shows that at the end you have this very nice result, which says that okay, with this, with good direction, with good sets of directions, we have the uniqueness property. And there is another result for Niva and Italian guys, which is very nice. But I don't have enough time to discuss it. Then let me skip to an open problem. Forget discrete tomography. I'm going to present you a puzzle. Okay. That you can forget everything that I said before. It's just a puzzle. Okay, we have these numbers from 1 to 8. Then in this case, n is equal to 8. And I'm going to put exactly the same number, same balls, in a bag from 1 to 8 with a red color. And then I'm going to, my input is some integers that I also put in the bag in green. And they are integers from 2 to 2n, but you can have some repetitions. For instance, you have 2, 9. And that's my input. And what I want to do is a matching with target sums. What does it mean? It means that I want to take a number, for instance 3, I put it with a 1 and I get a 4. And then I can take the 5, put it with a 2 and I get a 7. And I can keep doing this. And at the end, I have this matching with target sum. I use the red balls to obtain, I match them with the blue balls, and I get at the end the target sum that I wanted. That's the wanted solution. Of course, it's not always as simple as I've shown to obtain this solution. For instance, I can try like this. I put the 2 with the 7, I get the 9. I put the 3 with the 4, I get the 7, and I continue. Oh, I'm not able to have 15. Then I go back, I do like this. Oh, I'm no more able to use the 5. I'm stuck. Then I do it again, and then I get a new solution. Okay. Then, first question, what's the relation with discrete tomography? Why am I speaking about this? In fact, we are going to organize a little bit the things. I have my red balls, my blue balls, and then when I decide to put 8 with a 1, I can see that the sum is 9. It's like I put the 9 in the two-dimensional table. And if I match the 2 with the 2, I get the 4. And you can see that, in fact, this matching corresponds to putting the green values, my target sums, they are values that I'm going to put in my grid. And at the end, I will have a permutation matrix. Then, if I think about my problem, I want, for instance, I want 4. It means that I will select one cell which is on this diagonal, and I want 2, 9. It means that I'm going to select two values on this diagonal. And I don't want any 2, then I will 0. I want 0, 2 on this. And then, in fact, it means that my puzzle, my initial puzzle, it's exactly a discrete tomography puzzle. Exactly. It's the right puzzle that I have. And it's discrete tomography. But unfortunately, it's NPR'd, still NPR'd. But now I'm going to change a little bit the rule. Voila. That's exactly the puzzle that I already presented. And the little change that I'm going to do is, now, instead of doing the sum, I'm doing the sum in Zn. For instance, if I take the 5 and the 6, then n is equal to 8. Yeah. If I take the 5 and the 6, the sum is no more 11, it's 3. The sum mod 8. Then I'm playing exactly the same game, but if you think about that, it changes the diagonals. Then, if you take the diagonals with the 3, before it was very short, and now it continues on the right. Then you can think about it as diagonals on the torus. And then again, I can play this game. And then I have 2 7s, and it means that I want 2 on this diagonal. And the question is the same than previously. Does there exist solutions? Am I able to find solutions? And I can recall you that just before, without being in the Zn, it was NPR'd. And now there exist always solutions. That's amazing. You just skip from the classical framework to on the torus, and then there are always solutions. It's a result from 52. And there is a polynomial time algorithm to compute that. Now I arrive to Alon's question. Alon's question is really close, but it's not exactly the same problem. There's a small difference. Then I will take some, in my bag, I'm going to put some blue values, 0, 1, 4, 5, 6. These values, you don't have repetitions, because you want to put them on the left. And you have these values 0, 2, 2, 3, 5. You might have some repetitions because you are going to put them on the diagonals. And then I put my 0, 1, 4, 5, 6 on the left. It means that I know the projections. I know the horizontal projection. And for the vertical projection, it's 3. But I don't want it to be more than 1. Then it could be 1, it could be 0 vertically. It will be, at the end, it will be a subset of a permutation matrix. And the game is, I want then I have the diagonals, the diagonal projections, and the question is, do I have solutions? Does there exist solutions? And in fact, Nogueira only proved that, as in the previous case, there always exist solutions, always. And he proved it with Nullstellensatz. And the drawback of this is that it doesn't have any polynomial time algorithm to solve the problem. That's the issue. It knows that there is a solution. We know that there exists one, but we are not able to compute it in polynomial time. And that the open problem is to find a polynomial time algorithm to solve this question, this nice question. Then we have, on the left, a close result, where you have a polynomial time algorithm, and on the right you have something which it looks close, but you don't have any polynomial time algorithms. Then maybe there's something to do with this. Then, if you want to tackle this problem, don't hesitate. That could be. I don't believe that Nogueira alone. He knows a lot of things, but maybe this result of Marshall only he doesn't know it. Maybe. Then, as conclusion, let me go back to the initial question, which was to work over the 3D position of atoms. And in fact, it took much longer time than expected, but at the end, in Nature in 2011, there was these nice papers about reconstructing the position of atoms in 3D and with discrete tomography. And one of the main contributors is Jules Battenboot, that some of you might know. And you have these nice results. And that's the end of my talk. Thanks.
One question before lunch? Okay.
So I'm not an expert on this, and maybe my question is very naive, but regarding your last point, these Latin transversals, so I think that there are randomized algorithms that work in polynomial time somehow, and do you think that those could be used for you?
I don't know.
Okay.
Sorry. No, I really don't know.
All right.
Okay, let's thank the speaker again.
Jean.